Hello and welcome back. In this video, I want to introduce a conservation law for momentum. And to do this, I'd like to start by looking at an example. So in this example, we have two masses that are moving towards each other as they fall to the ground. And so what I'm showing here is sort of a time lapse of what's going on. So initially we have mass 1 on the left, which is moving to the right, and mass 2, it's on the right, and the mass is moving to the left. Now after a certain amount of time passes, the two masses collide. So mass 2 exerts a force on mass 1, and mass 1 exerts a force on mass 2. And then still some time later, the two masses are moving off in different directions. So what I'd like to do is I'd like to apply the impulse momentum theorem to mass 1 and mass 2. So the impulse momentum theorem, remember this says that the impulse is equal to the change in the momentum. So the impulse that's exerted on mass 1 is equal to, remember impulse is force times delta t. So the forces that were exerted on mass 1 are the force due to gravity that was exerted on mass 1 plus the force that mass 2 exerted on mass 1. So we take the sum of those forces and multiply it by delta t to find the impulse that was exerted on mass 1. And this has to equal the change in momentum of mass 1. Doing the same thing for mass 2, we see that the impulse that's exerted on mass 2 is equal to the change in the momentum of mass 2. And the total impulse that's exerted on mass 2 is the force due to gravity that's exerted on mass 2 plus the force that mass 1 exerts on mass 2 times delta t, and this has to equal the change in the momentum of mass 2. So now what I'd like to do is I'd like to consider the sum of these two. So I'd like to look at the total impulse, that is the impulse exerted on mass 1, plus the impulse that's exerted on mass 2. And we know from the impulse momentum theorem that this has to equal the change in the momentum of mass 1 plus the change in the momentum of mass 2. So just going back to the formulas that we found, the impulse that was exerted on mass 1 is the force due to gravity exerted on mass 1 plus the force that mass 2 exerts on mass 1 times delta t. So this right here is just the impulse that was exerted on mass 1 plus the impulse exerted on mass 2 is the force due to gravity exerted on mass 2 plus the force that mass 1 exerts on mass 2. Take all of that and multiply it by delta t. So this stuff right here is just the impulse exerted on mass 2. And according to the impulse momentum theorem, this is equal to the change in the momentum of mass 1 plus the change in the momentum of mass 2. So now what I'd like to do on the next line is I'd like to rearrange this line above, grouping the forces together a little bit differently. So I'm going to write this as the force due to gravity that's exerted on mass 1 plus the force due to gravity that's exerted on mass 2 times delta t plus the force that mass 2 exerts on mass 1 plus the force that mass 1 exerts on mass 2 times delta t is equal to the change in the momentum of mass 1 plus the change in the momentum of mass 2. And so now what I'd like to do is I'd like to rename these different things. So if we look at this grouping that I have over here on the left, this is what I'm going to call the external impulse. And I call this the external impulse because this is the impulse that is caused by the force of the Earth pulling on the two masses. Right? The force due to gravity is caused by the Earth pulling on mass 1 and pulling on mass 2. And the reason that I call this an external force is because I don't consider over here on the right the effect that this has on the Earth. So when mass 1 is falling to the ground, it's going to pull on the Earth, and I don't consider that in here. So I'm going to call this an external force. And these two forces here, the force that mass 2 exerts on mass 1 and the force that mass 1 exerts on mass 2, I'm going to call these internal forces. These are internal because mass 1 and mass 2 are both of the masses that I'm considering when I look at the effect that they have on the system. Right? So I'm looking at the change in the momentum of mass 1, and I'm looking at the change in the momentum of mass 2. So these two masses are internal to the system. And then finally, I want to call this thing here, the change in the momentum of mass 1 plus the change in the momentum of mass 2. I'm going to call this the change in the total momentum. So what we have is we have that the external impulse plus the internal impulse is equal to the change in the total momentum. But at this point, I'd like to point out something that's very important. The force that mass 2 exerts on mass 1 and the force that mass 1 exerts on mass 2 are related by Newton's third law. Newton's third law tells us the force that mass 2 exerts on mass 1 is minus the force that mass 1 exerts on mass 2. So the sum of these two things is always going to be 0. So the internal impulse in any system is always 0. So what this tells us is it tells us that the sum of the external impulses is going to equal the change in the total momentum of the system. And an immediate result that we get from this is that when there are no external forces present in the system, the change in the total momentum is always 0. And this result is called the conservation of momentum. So before we look at any examples, I'd like to just address a question that very commonly comes up when we start studying conservation of momentum. So before I said that the total momentum is going to be conserved when there are no external forces present. So going back to this previous slide, we have that the sum of the external impulses is equal to the change in the total momentum. So the total momentum is going to be constant only when there are no external forces. However, in a lot of the examples that we'll be looking at, we will be using conservation of momentum even though there are external forces present. So I'd like to sort of explain why it is that we can do that. And to do this, I'd like to look at two different examples. So the first example I'd like to look at is what happens when a pitcher throws a ball from the pitcher's mound to a batter. So when this happens, so the ball is going to be moving to the right like this, and there's a force due to gravity that's going to be pulling down on the ball. So when a pitcher throws a ball from the pitcher's mound to the batter, the force due to gravity pulls down on the ball, causing it to change direction. So when this happens, the momentum of the baseball changes as it moves from the pitcher's mound to the batter. So the momentum of the baseball will not be conserved as it moves from the pitcher's mound to the batter. However, if we look at what happens when a baseball hits a bat, so let me kind of draw a picture of what's going on here. So when a baseball hits a bat, the bat is going to exert a force on the ball. So this is the force that the bat exerts on the ball. And then the ball is going to exert a force on the bat. And because a baseball is in contact with a bat for just such a short instant of time, so such a small fraction of a second that the baseball is actually going to be in contact with the bat, it turns out that the impulse that is exerted by gravity when a baseball is in contact with a bat is going to be very, very small, because it's the force due to gravity times delta t, and this delta t is going to be very, very small. However, we know, right, when a baseball hits a bat, the change in the momentum of the baseball is very large, and the change in the momentum is almost entirely caused by the baseball hitting the bat. Right? So if a baseball hits a bat and it's traveling 100 miles per hour, when it hits the bat, it's going to be traveling in the opposite direction at approximately the same speed. So the change in the momentum, so if we kind of think about this, so the impulse that is exerted from the bat, so let me write this as the impulse that is exerted by the bat on the ball is equal to the force that the bat exerts on the ball times delta t. And this is approximately going to be equal to the change in the momentum of the ball, because almost all of the change in the momentum is going to be caused by the ball hitting the bat. And we know that this is pretty large. So what this tells us is it tells us that the impulse that is caused by the bat hitting the ball is much, much larger than the impulse that is caused by gravity if we just look at the moments immediately before the ball hits the bat and immediately after the ball hits the bat. So a lot of times when there is some type of collision like this between two objects, if we look at the momentum immediately before the collision and then immediately after the collision, even though there will be some external forces, such in this case, gravity is still pulling down on the ball, even when it hits the bat, we can ignore that force because the impulse that's caused by that force over this extremely short period of time is going to be negligibly small. So that's why we can use conservation of momentum even when there are external forces present, as long as we're looking at the momentum immediately before and immediately after some event. So let's go ahead and look at a couple of examples. This first example says, two ice skaters with a mass of m1 and m2 push against each other and move in opposite directions. Eventually, friction brings the two skaters to rest. Skater 1 glides twice as far as skater 2. Assuming the coefficient of friction is the same for both skaters, what is the ratio of their masses? So the basic idea behind this problem is that when the two skaters push off of each other, the skater who has less mass will be moving faster, and the skater who has more mass will be moving slower. So as a result, the skater who has less mass is going to glide further than the skater who has more mass. So we're told that skater 1 glides twice as far as skater 2, so skater 1 will have less mass than skater 2. And we'd like to figure out how this distance is related to those two masses. So the first step in solving this problem is figuring out how the masses of the skaters are related to that initial velocity that they have immediately after they push off of each other. So to do this, let me kind of just draw a picture of what's going on. So initially, the skaters are going to be at rest. So the two skaters are standing there on the ice, holding hands, and then immediately after, the two skaters push off of each other. The two skaters will be moving in opposite directions, which I'll call this V1 and V2. And we'd like to figure out how these two velocities are related to the masses of the two people. And the way we can do this is by using conservation of momentum. And the reason we can use conservation of momentum is that during this time that the two skaters push off of each other, the force that the two skaters exert on each other will be much, much greater than the frictional force that is exerted on the two skaters. So we can ignore the effect of the frictional force just for this moment when the two skaters are pushing against each other. So as a result, the only two forces we're looking at is the force that skater 1 exerts on skater 2 and the force that skater 2 exerts on skater 1. So we can ignore the external forces and just look at the internal forces. So we can say that the initial momentum, the initial total momentum, is going to be equal to the final total momentum. And initially the two skaters are both at rest, so the initial momentum is 0 kilogram meters per second. And the final momentum, well, the momentum of person 1 is going to be m1 v1, and the momentum of skater 2 is going to be m2 v2. And these two things are going to add up to 0 because the two skaters are moving in opposite directions. So these two vectors will be pointing in opposite directions. So this is going to happen when m1 v1 is equal to m2 v2. Here I've dropped the vector signs, and because they're pointing in opposite directions, I don't have to worry about that negative sign that'll appear when I move one to the other side of the equation. So I'm looking for m1 divided by m2, and according to this, that's going to equal v2 over v1. So now what I need to do is figure out how this initial velocity that they have immediately after they push off of each other is related to the distance that they travel before coming to rest. So to do this, I need to apply Newton's second law. So when the skater is moving immediately after they push off of each other, there are three forces that are acting on the skater. There is the force due to gravity pushing down on them. There is the normal force that the ice exerts up on the skater, and then there's this frictional force that's slowing down the skater. And this frictional force is going to be opposing the velocity of the skater. So in this case, we have the velocity pointing to the left, we have the frictional force pointing to the left, so this is if the skater were moving to the right. So if we apply Newton's second law to the skater, we have that the frictional force that is exerted on the skater is equal to their mass times acceleration. And the frictional force, remember, is mu times the normal force. And in this case, the normal force is equal to the gravitational force. So we have the frictional force is mu mg, and this has to equal mass times acceleration. So in this problem, the masses cancel out, and we see that the acceleration of the skater is just mu times g. So what this means is that the acceleration of the two skaters is going to be the same. It doesn't matter what their masses are, because mass appears on both sides of this equation, right? The more massive the person was, the larger their frictional force, but the larger the mass is, the smaller their acceleration will be, because F equals ma. So now we know how the acceleration is related to the coefficient of friction in gravity. What we can do is we can use kinematics to relate the initial velocity to the distance that they travel. So immediately after they push off of each other, they're going to be moving with some velocity, and I'm going to call that the initial velocity. So this is the velocity they're moving right after they push off of each other. And then the final velocity is the velocity once the skaters come to rest. So this is 0 meters per second. And so I'd like to relate this initial velocity, the final velocity, and delta x. So the way we can do this is by using the equation v final squared is equal to v initial squared plus 2a delta x. And in this case, the final velocity is 0. So we have that v initial squared is minus 2a delta x. And if we think about the two skaters, the acceleration always points in an opposite direction as delta x. So when we multiply these two things together, when we multiply the acceleration by delta x, we're always going to get a negative number. That'll cancel that negative sign there. So I'm just going to kind of ignore the directions of these things and drop that negative sign. So we have that the initial velocity is going to be equal to the square root of 2a delta x. So this is how the velocity of the skaters immediately after they push off of each other is related to the distance that they travel. So in this previous slide, we said that m1 over m2 is equal to v2 over v1. So we have m1 over m2 is equal to v2 over v1. And we also found in this slide that the velocities of the skaters, this is the velocity immediately after they push off of each other, is proportional to the square root of 2a times the distance that they travel. So here we have the square root of 2a times the distance that skater 2 travels divided by, here we have 2a times the distance that skater 1 travels. And now what I can do is the 2's are the same, so I can cancel this out. The accelerations of the two skaters are the same. Remember, the acceleration was just mu times g, so that's going to be the same for both skaters as well. So we can see that the ratio of the masses is just equal to the ratio of the square root of delta x2 over delta x1. And since skater 1 travels twice as far as skater 1, the number in the denominator is twice as big. So we have the ratio of the two masses is 1 over the square root of 2. So let's go ahead and look at another example. This example says a 98 kilogram man is standing still at one end of a floating log which is initially at rest. The log has a mass of 230 kilograms. The man runs to the other end of the log, moving at 3.6 meters per second. He then hops onto an identical floating log which was initially at rest. And the question asks us to determine the mass of the first log immediately after the man jumps off of it, and then the velocity of the second log after the man lands on it. So looking at this first scenario where the man's jumping off of the first log, initially the man is going to be at rest and he'll be standing on a log which is also at rest. So initially the total momentum of the system is going to be equal to 0. Now, immediately after the man jumps off the log, the man is going to be exerting a force on the log, pushing it in one direction, and the log will exert a force on the man, pushing him in the opposite direction. And these forces that the man exerts on the log, and the force that the log exerts on the man, is going to be much greater than the frictional forces that are involved. So we can say that the momentum immediately after the man jumps off of the log is going to be equal to the initial momentum of the system. So we have that the final momentum of the man plus the final momentum of the log is going to be equal to the initial momentum of the total system, and that this is equal to 0 kilogram meters per second. So we have the final momentum of the man plus the final momentum of the log is equal to 0. And remember that momentum is equal to mass times velocity. So the final momentum of the man is the mass of the man times the final velocity of the man. And the final momentum of the log is the mass of the log times the final velocity of the log. And the sum of these two things has to equal 0 kilogram meters per second. So solving for the final velocity of the log, we see that the final velocity of the log is going to be equal to minus the mass of the man divided by the mass of the log times the final velocity of the man. And if we plug numbers into this, we see that it's equal to minus 1.53 meters per second, where this minus sign here indicates that the log will be moving in the opposite direction that the man is moving in when the man jumps off of the log. Now looking at the second situation, initially the man is going to be moving with some velocity. This is 3.6 meters per second. So initially the man has a momentum that's equal to the mass of the man times this 3.6 meters per second. And the log initially has 0 momentum, because the log that the man's going to jump on is initially at rest. Now, after the man lands on the log and the log are going to be moving off with the same velocity, because the man's going to be standing still on this log. So what we can say is that we can say that the final momentum of the total system is going to be equal to the mass of the man plus the mass of the log times the final velocity of both the man and the log. So they're going to be moving with that same velocity. So setting the initial momentum equal to the final momentum, we have the mass of the man times his initial velocity, and that's this 3.6 meters per second, has to be equal to the final momentum, and that was the mass of the man plus the mass of the log times the final velocity. So solving for this final velocity, we see that the final velocity is going to be equal to the mass of the man divided by the mass of the man plus the mass of the log. All of this times the initial velocity that the man was moving before he landed on the log. And if we plug all the numbers into this, we see that it's going to be equal to 1.08 meters per second. And in this case, this velocity is positive, which means the velocity of the log is going to be in the same direction that the velocity of the man was just before he landed on the log. Now, in all of the examples we've looked up until now, we've only been looking at conservation of momentum in one dimension. But it's important to remember that momentum is a vector. So when we say that the sum of the initial momentums are equal to the sum of the final momentums, what this actually means is that we have conservation of momentum in the x direction and conservation of momentum in the y direction. So let's look at an example where we use this. This example says a firework is initially moving vertically upwards with a speed of 45 meters per second. The firework suddenly breaks up into two equal pieces that move with a speed of v1 and v2. So I have v1 here is at an angle of 30 degrees with respect to the vertical, and v2 is at an angle of 60 degrees with respect to the vertical. Now, just like in the other problems, we can use conservation of momentum. The reason we can use conservation of momentum is that the explosion that causes the rocket to break up into these two pieces will occur over an extremely short period of time. So we can ignore the effects of gravity over this short period of time, and we can say that the momentum immediately before the explosion and immediately after the explosion will be the same. Now, because these two pieces are moving off at different directions like this, we will have to use conservation of momentum in the x and y directions. So this will give us two different equations that we can use, and we can use these two equations to solve for the two unknowns, v1 and v2. Now another thing I should mention is that we're told that the rocket breaks up into two equal pieces. So this means that the mass of both of these pieces will be equal, and I'll call those masses m. Now what this also means is that the initial mass of the rocket will be 2 times m, because it's both of the pieces put together. Now, because we're looking at conservation of momentum and the x and y directions separately, we need to figure out how the x and y components of our velocities are related to these angles and the speed that the pieces are traveling at. So, looking at this piece 1, we can see that the x component of v1 is opposite the angle of 30 degrees. So we see that the x component of v1 is equal to v1 times the sine of 30 degrees. And the y component of v1 is v1 times cosine of 30 degrees. It'll be cosine because it is adjacent to the angle 30 degrees. Now looking at the x component of v2, we can see that this is opposite the angle 30 degrees. So this will be v2 times the sine of 60 degrees. And we can see that the y component of v2 is adjacent to the angle 60 degrees. So we have vy2 is going to be v2 cosine of 60 degrees. So again, we have conservation of momentum in the x and y directions separately. So the first thing I want to look at is conservation of momentum in the x direction. So if we think about this rocket, initially the rocket is moving vertically upwards. So initially the velocity in the x direction is 0. This means that the initial momentum of the rocket in the x direction is 0 kilogram meters per second. So conservation of momentum tells us the sum of the momentums, the final momentums in the x direction, are equal to the initial momentums in the x direction. And the initial momentum of the rocket in the x direction we said is 0 kilogram meters per second. Now, the sum of the final momentums of the two pieces in the x direction, remember momentum is mass times velocity, so one of the pieces has a momentum of m times v1 in the x direction, and the other piece has a momentum of m v2 in the x direction. And when we add these together, we have to get 0 kilogram meters per second. Now, because the rocket breaks up into two equal pieces, these two masses are the same, so I can divide those two things off, and then I get that v1 in the x direction is minus v2 in the x direction. Now, since I want to relate these things back to the speeds that they're traveling at, I want to rewrite these in terms of the speeds. So we said that v1 in the x direction is v1 times the sine of 30 degrees. And this is minus v2 sine of 60 degrees. So solving for v1 in terms of v2, we see that v1 is going to be equal to minus v2 times the sine of 60 degrees divided by sine of 30 degrees. So this is the first equation that we get. So now let's look at conservation of momentum in the y direction. So again, going back to this picture here, the rocket is initially traveling vertically upwards with a speed of 45 meters per second, and the initial mass of the rocket is twice the mass of either one of these two pieces. So again, we have that the sum of the final momentums in the y direction are equal to the initial momentum of the rocket in the y direction. And the initial momentum of the rocket in the y direction, we said that this is 2m times, let me just call this v0. This is the initial velocity of the rocket. And the final momentum of the two pieces, so one of the pieces is going to have a final momentum, let me just write this as m v1 in the y direction, and the other will have a momentum m v2 in the y direction. And again, we want to rewrite these in terms of the speeds that the rocket's traveling at. So this is going to be, actually, let me go ahead and divide off the masses before I do anything else. And now let me rewrite these two things in terms of the speed and the angle that they're traveling at. So this is going to be v1 times cosine of 30 degrees. And this is going to be v2 times cosine of 30 degrees. And this has to equal 2 times v naught. And in the previous slide, I found that v1 is minus v2 times sine of 60 degrees divided by sine of 30 degrees. So if I plug that in here, so we have, this was v1 is equal to this. So we have v1 is actually equal to minus v2 times sine of, let me make sure I get this right, it's 60 degrees divided by sine of 30 degrees. So what I've done here is I've just plugged in to this formula this equation that we found on this previous slide, where we found v1 is equal to minus v2 times sine of 60 degrees divided by sine of 30 degrees. So I've plugged that into this equation here. So we have that's v1, so this whole thing here is just v1 times cosine of 30 degrees plus, then we have v2 times cosine, oh, it should say 60 degrees, times cosine of 60 degrees is equal to v naught. So now at this point, I have an equation that only has one unknown. We've got v2. So anytime you have an equation with just a one unknown, you bring everything that has that unknown to one side, and then you factor it out. So right now we've got v2, it's all on the left side, so I'm going to factor out the v2 from everything. So I have v2 times, so this is going to be minus sine of 60 degrees divided by sine of 30 degrees times cosine of 30 degrees plus cosine of 60 degrees equals to v naught. And it turns out that if you plug all of this stuff into a calculator, this cosine of 60 degrees minus the cosine of 30 degrees times sine of 60 degrees divided by sine of 30 degrees, if you type all of this mess into a calculator, it turns out that this whole thing here, in parentheses, is just equal to 1. So what you wind up getting is you find that v2 is equal to 2 v naught. So that's going to be 2 times 45 degrees, so v2 will be 45 degrees, 45 meters per second. So we have that v2 is equal to 90 meters per second. And then finally, if we want to, we can plug this number back into this equation right here, and we can solve for v1. So if we do that, we said that v2 was 90 meters per second, so we plug 90 meters per second into here, and we multiply that by sine of 60 degrees divided by sine of 30 degrees, and if we do that, we see that this is going to be equal to minus 77.9 meters per second. So this is the velocity of piece 2. And so I think at this point, I'd like to end this video. And in the next video, I want to talk a little bit more about collisions. So we'll talk about different types of collisions, and then we'll work through some examples.